Jain to all. Today I'm here to present the video lecture on the subject control system BEC 602. I am Dr. Amit Garg, Associate Professor in EC Department of Akgec Garg Engineering College, and the topic is polar plot and Nyquist plot. So in this particular video lecture, we will see that what is polar plot and Nyquist plot, and we will also see some of the associated problems. So let us start with the polar plot. You can say this Nyquist plot is basically the closed plot and polar plot is the open plot. Okay, so let us start with the polar plot. So the presence of magnitude plot and phase plot for showing the variation of gain and phase angle of a system with respect to the change in frequency is the major disadvantage of the Bode plot. So look, we have already seen this Bode plot. So in case of Bode plot method, we have to draw the two plots. So one plot is magnitude plot, where we will draw the magnitude with respect to the frequency, and another one is the phase plot, where we will plot the phase angle with respect to the frequency. Okay, and so we have to use two plots. Okay, but in case of polar plot, the plot that combines both the plots in a single plot without losing any information is called polar plot. Okay. So in polar plot, what we are doing basically, we are combining these two information. Okay. So when we are combining these two information, so that for a particular frequency, we are having the value of magnitude as well as phase angle corresponding to that frequency value. So the polar plot can be plotted either on a polar graph or on an ordinary graph. Generally, we will plot it on ordinary graph by choosing some appropriate scales. Okay. So the polar plot of a loop transfer function, open loop transfer function Gj omega H j omega is defined as a plot of magnitude of Gj omega versus angle of Gj omega H j omega on the polar coordinates, as the frequency omega varies from 0 to infinity when it is plotted on a polar graph. So simply what we will do, we are having, like, situation is this, you can say, understand, this is your point where the magnitude is 0 and phase angle is 0. Okay, so 0, angle 0. So whenever we will write it like m angle phi, m angle phi. Okay, so here at this point 0, angle 0, and we are moving like here to here. So at this point, what happen? Magnitude will be some value and phase angle will become plus 90 if we are moving in this direction. And if we are moving in this direction, so this is the magnitude. Let's say this one was m1, this is m2, angle is minus 90 degree, and like this. Okay. Now we have given one question, obtain the polar plot of given open loop transfer function GSHS equals to 1 upon 1 plus T1S into 1 plus T2S. So how we will solve it? So first of all, we will put simply S equals to J omega in this equation. So it will become G J omega H J omega equals to 1 upon 1 plus T1 J omega into 1 plus T2 J omega. Okay, we have simply put S equals to J omega here in this transfer function, open loop transfer function. Then we will calculate the magnitude. So mod of G J omega H J omega equals to 1 upon under root 1 plus here omega square T1 square under root 1 plus T2 square omega square. You know this. Mod of G J omega H J omega equals to 1 upon under root of real part ka square plus imaginary part ka square into under root of real part ka square plus imaginary part ka square. Okay. Now we will calculate the phase angle phi, which is nothing but tan inverse. You can write it like always 1 plus J0 to 1 plus J0. So here angle will become tan inverse 0 by 1. Here angle will become tan inverse omega T1 by 1. Here tan inverse omega T2 by 1. Okay. So this will become tan inverse 0 will become 0 degree. So phi will become 0 degree minus tan inverse omega t1 minus tan inverse omega t2. Okay, so this is the phase angle phi. Now what we will do, basically we will vary the frequency from 0 to infinity and check that how the magnitude and phase angle will vary when we will change the frequency from 0 to infinity. Okay, so like we can do one thing, we can make a table like this. Here is omega, here is magnitude, and here is the phase angle. Always first value at omega equals to 0, you can see at omega equals to 0, the magnitude will become, from here you will see magnitude will become 1, because this will become 0, this will become 0, so magnitude will become 1. And at omega equals to 0, if you will see the phase angle, this is minus tan inverse 0 minus tan inverse 0. Okay, so it will become 0 degree. And combinedly you can write it like 1 angle 0 degree. Okay, and you can take some another frequencies, like if you will choose, let's say omega equals to 10. When omega equals to 10, you will get certain value of magnitude, and also you will get certain values of phase angle, and then you can combinedly write it like this. Now if you will choose omega equals to 1 by t, let's say you are choosing point omega equals to 1 by t, where t is the time constant, we don't know the value, but let's say if omega equals to 1 by t. So if you will see here at omega equals to 1 by t, it will become 1 by t1 square. So it will become 1 plus 1 into under root 1 plus 1. It means 1 by root 2 into root 2. It means 1 by 2. And here you will put omega equals to 1 by t1. So it is minus tan inverse 1 and minus tan inverse omega equals to, sorry, 1 by t1 if we are taking here. So it is minus tan inverse 1 minus 45 minus tan inverse omega 2 to 10 minus tan inverse omega t2. You can solve it. Okay. So similarly, you can find out now at last, you will find the value at omega equals to infinity. When omega equals to infinity, you know, this term will become 1 by 0. So it will become, magnitude will become infinity. Sorry, magnitude will become when omega will become infinity. So this will become 1 by infinity, it means 0. And here minus, what happened? Minus tan inverse infinity minus tan infinity. It means minus 180 degree. So you can see in this table, and when omega tends to 0, we are having the value 1 angle 0, and when omega tends to infinity, this is 0 minus 180. So we can find out the intermediate values if required. Otherwise, intermediate values are not required. We have to simply see the angle of rotation. So if you can see the angle of rotation at will be minus 180 degree minus 0 degree. It means minus 180 degree will be the angle of rotation. Minus 180 degree means clockwise rotation by 180 degree. Okay, 180 degree clockwise rotation means we will go from source to destination. Source is this, destination is this, and we will take an angle of minus 180 degree. Okay, so can we plot it now? You can see this. This is 1 angle 0. Let's say this point is 1 angle 0 degree, and this is 0 angle minus 180 degree. Because magnitude 0, so this point is there. But we have to move minus 180 degree clockwise direction. So it means we have to make from this point to this point an angle subtend will be 180 degree, minus 180 degree. So that's why this plot is somewhat like this. So polar plot you can see here given in this figure. And if you want to calculate the parameter, if you want to calculate the value of this point, if somewhere it is required, then you can easily calculate it. How you will calculate it? You have given the transfer function. What you will do? You will multiply its by its conjugate to rationalize it. Once you will rationalize, so you are having real part and imaginary part separated with each other. Now, because this point is located on imaginary axis, then what you will do? You will put the real part equal to 0. You will put the real part equal to 0, and by putting that real part equal to 0, you will get the frequency. And that frequency value, if you will put in imaginary part, you will get this distance. So you can easily find out this distance also if it is required, if it is given in the question, or you want to calculate it for any other sense. Okay. And this was the simple polar plot. Another one is draw the polar plot into a system is stable and its gain margin and phase margin. So here in this particular question, we are also interested in gain margin and phase margin, which are two parameters which is used to define the relative stability of the system. For a system to become stable, both gain margin and phase margin must be positive, and the corresponding frequencies like gain crossover frequencies and phase crossover frequencies, situation is like phase crossover frequency should be greater than gain crossover frequency. If it is not so, then the system will become unstable. So what we will do, we will put S equals to j omega in this particular equation. So it is 12 by j omega times 1 plus j omega into 2 plus j omega. Now we will calculate the magnitude, which is 12 upon omega under root 1 plus omega square under root 4 plus omega square, and phase angle is nothing but corresponding to this it is 0 degree, 9 minus 90, tan inverse minus tan inverse omega by 1 minus tan inverse omega by 2. Now, starting point is 0 and end point is infinity. Okay. So, when omega equals to 0, this magnitude will become infinity from here you can see, and when omega equals to 0, it will become phase angle is minus 90 degree. And when omega equals to infinity, magnitude equals to 0 and phase angle will become minus 90 and minus 90. It will become minus 270. Okay. So, the angle of rotation in this case will become minus 270 minus of minus 90 degree. It means minus 180 degree clockwise rotation. Okay. So, like if you want to draw this plot, it is somewhat like at omega equals to 0, magnitude is infinity and phase angle is minus 90 degree. So, you can say somewhere here you are having infinity minus 90 degree angle, and omega equals to infinity means m equals to 0 here, and phase angle is minus 270. So, this is minus 90, minus 180, minus 270. So, this line is, you can say this point is 0 minus 270 degree, but 270 degree angle line is this, and we have to rotate minus 180 degree in clockwise direction. This is the starting point and this is the end point. So, this possibility is like, we can make it in a better sense. So, this is the polar plot. Okay, this is the general shape of the polar plot. Now, we are interested in this point. We are interested in this point at which our polar plot cuts the negative real axis. So, what we will do? We will rationalize it. Rationalize it means by multiplying the conjugate of this denominator. Okay, so it will become minus j omega, 1 minus j omega, 2 minus j omega, and you will also multiply it in the numerator side. Okay, and when you will solve it, you will find, when you will separate it, like this is the real part you are getting and this is basically the imaginary part you are getting. Now, you are interested in this point. At this point, what happened? There is no imaginary part. So you will put this imaginary part equal to 0, particularly 2 minus omega I square equals to 0. So from here we have find out the phase crossover frequency. This is called as the phase crossover frequency at which the polar plot cuts the negative real axis. Okay. So this is the phase crossover frequency. Now we want to get this distance. This is, let's say, O, this is the Q. So if you want to get this distance, then what you will do? You will put the value of omega here in this particular portion. So when you will put omega equals to omega PC equals to root 2, we have calculated. So when you will put it over here, it will become minus 36 upon 1 plus 2 into 4 plus 2, 6 into 3, 18. So it will become minus 2. Minus 2 means it will cut at negative axis at minus 2 point. So this is the exact plot. This is the, you can see the exact plot, that is the approximated plot that I have drawn. Okay. So gain margin is nothing but 1 upon mod of OQ. And if you want to get this value in magnitude or in dB, then you will take 20 log. So you will get minus 6.02 dB. So you can see here the gain margin is negative. So definitely your system will become unstable. But for finding out the value of gain crossover, you can do one thing at gain crossover frequency, magnitude of G j omega H j omega equal to 1 at omega equals to omega g. This is the analytical method. This is analytical method by which you can solve. And once you will get this value at omega equals to omega gc, when you will put this value in the angle, you will get the phase margin. Okay. Another thing is that, like, you will draw it correctly on a plot. When you will correctly draw on a plot, you are getting the frequency. This frequency. Plot starts from here. So what is the frequency here? This is nothing but omega gain crossover. Okay. So you will get this omega gain crossover, and with the help of omega gain crossover, you can find out the omega phase margin. And phase margin in this case is minus 17.5 degree. As gain margin and phase margin both are negative, and the system is the unstable system. Okay. Now we will see the Nyquist stability gradient. Now, the Nyquist stability gradient will be useful in analyzing the stability of both the open loop and closed loop systems. The concepts such as encirclement, enclosement, number of encirclements around a point, mapping from one plane to another plane, and principle of argument are important to study the Nyquist stability criterion of the system. So it is derived by H. Nyquist. It is a semi-graphical method that helps in determining the absolute distributed control system graphically from frequency response of loop transfer function without determining the closed loop poles. The Nyquist polar plot of a loop transfer function is a graphical representation of the frequency response analysis when the frequency omega is varied from minus infinity to plus infinity. So Nyquist plot helps in determining the relative stability of the system in addition to the absolute stability of this. So there is some issue with this polar plot analysis. In case of polar plot analysis, what happened when you are having a complicated type of point? So it will become complicated type of plot. Then it is difficult to find out whether a particular point is enclosed or not. If minus 1 plus j0, which is a critical point, if it is not enclosed, then we can say system we cannot find out the stability using polar plot. So alternative method is Nyquist method, which is more concrete method, which is a closed loop, and in this case, by checking the encirclement, net encirclement of minus 1 plus j0 point, we can find out the stability. So I am not going through the much details of the theory. I am going with an example. Let us suppose this is the transfer function given to us. We have to determine the range of values of k for which the system is stable. So first of all, we have to find out that how many poles of this transfer function, open loop transfer function, are lying on right half of the S plane. So you can see both poles are at s equals to minus and s equals to minus 1. So there is no pole. So it means p equals to 0 because there is no pole lying at the right half of the S plane. So the condition of stability is n equals to z minus p because there is no 0 and there is no pole. So n equals to minus p equals to 0 is the condition for stability. Now we will put S equals to j omega in this equation, and we will also draw the Nyquist path. You can see Nyquist path, because there is no pole at origin or imaginary axis, so Nyquist path is like this. So you can say your Nyquist path is a path which starts from plus j infinity, will pass from s equals to 0 and reach till s equals to minus j infinity, and then again from minus j infinity to plus j infinity with a semicircle of infinite radius. Okay. So put s equals to j omega in this equation and take this section. This is the first section, this is second section, this is section 3. Section 1 and section 2 are mirror image of each other. So we will do the analysis of only section 1. And section 3, when you will analyze, you will find it is nothing but an origin. It is nothing but the origin. So first we will check this analysis of plus j infinity to 0. So s equals to plus j infinity to s equals to 0. We will see when we will find out the magnitude. So magnitude will become magnitude when you will put s equals to j omega here and omega tends to infinity. So magnitude will become here, you can write 4 plus omega square upon 1 plus omega square. So when omega tends to infinity, it will become 0. And when omega equals to 0, it will become, you can see 2k. It will become 2k, you can see from here. And angle, in first case, this angle is, you can say 90 degree, and this is 90 degree, and this is 90 degree. Tan inverse infinity, and tan inverse minus 2 plus j infinity. Minus 2 plus j infinity means in this quadrant somewhere here. So angle when you are making, when this point is tending to infinity, so this angle is 90 degree. It is important to note. So this is 90, 90, 90. So it is 0 minus 90. And similarly for omega equals to 0, what happened? Minus 2 plus j0 minus 2. This is not point. So this angle is 180 degree. So here 180 degree, 0 degree, 0 degree. So 2k, angle 180 degree. So the anticlockwise rotation will be anticlockwise plus 270. So second is mirror image of section 1 about real axis. Section 3 not required as it is an origin. Now what we will do? We will do the rationalization. So rationalization, so we will multiply by 1 minus j omega into 1 minus j omega in denominator and as well as in numerator. Okay. So by solving this, when you will solve it, you are having this portion. So this is the imaginary part, this is the real part. You will put real part, imaginary part equal to 0. So it is 5 minus omega square equals to 0. It means omega equals to root 5. Now put this value omega equals to root 5 in this real part. So you are having the point at which the Nyquist plot will cut the negative real axis. So when you will solve it, it is the value k by 2. It means this is the point at which it will cut. So the positive at k equals k by 2. So when you will solve it, it is plus k by 2. Sorry, so it is plus k by 2. It means it will cut over here. Okay, and not the negative real axis, and it is not cutting the negative real axis. So Nyquist plot is like here. Like you can see, the first value is 0 and then 2k. Angle of rotation is plus 270. Yani 0 2k, 0 to 2k angle plus 270. Plus 270 means you have to make a plot, means this is the plus 270. Okay, so that's why this plot will start. This plot will start sorry. Plus 270, it means, yeah. This is the polar plot for the section 1. It will start from 0 till reach as 2k. and angle of starting from minus 90 and terminate at angle 180 degree in positive direction. So that's why 270-degree angle can be made by this. And section 2 is the mirror image. It means you can say it will be the mirror image of this. Okay, and this point is 2K. So for n equals to 0, minus 1 plus j0 point should not be encircled, must lie to the left of the point P. This is the point P, and because the number of encirclement of this point is 0, so this point should not be encircled. So when this point will not be encircled, when minus 1 plus j0 point will be somewhere lying here, only then it is possible. It means length of this, which is nothing but minus 2K, will be less than 1. So from this you can get the value of K less than 1 by 2. So for stability, K should be less than 0.5. So this is the range of stability of K for the system to become stable. And another is sketch the Nyquist flow system open loop transfer function is this. You can see here two poles are lying at right half of the S plane, and there is also a 0 at S equals to 0. Okay, so two poles, it means P equals to 2, and N equals to minus P, it means it equals to minus 2. Okay, and so this is the Nyquist path. It will not pass from here, and put S equals to j omega in this equation and rationalize it. So when you will rationalize it and you will take the section, first section is at plus j0, another section is at minus j0. So there are three sections, 1, 2, 3 and 4. 1 and 3 are mirror image of each other. 1 and 3 are mirror image of each other. 4 is basically an origin. So we'll analyze the section 1 and section 2. So section 1, we are having minus 90-degree angle, and 0 minus 180, 0 minus 270. And here 0 minus 270 and 0 minus 450. Okay, or you can say minus 180-degree clockwise direction. So if we will see it, this is basically the Nyquist plot for this. And intersection with negative real axis, we will multiply with the conjugate, then we will rationalize it, then we will put this value equal to 0 to find out the phase crossover frequency. When we will put this phase of crossover frequency, we will get the point at which it will cut the negative real axis. So it is minus 0.09374. Okay, like here you can see this is the point. This is the point. So you can say this value is less than 1. So it means minus 1 plus j0 will be somewhere lying here. Okay. So section 1, you can say 0 minus 180 and 0 minus 270, and within rotation of minus 90. Okay. So 0 minus 270 and 0 minus, it means a point which is starting from somewhere here and terminating over here. But it is also cutting this point over here. Okay, so you can say it is like this, and its mirror image is like this, and you can say, yeah, this is the complete diagram. Okay. The Nyquist plot is shown. Note that while approaching from 0 minus in clockwise, section 1 of plot has to intersect point Q. Then it will travel through third quadrant, and through point Q will reach to 0 minus 270. So for stability, n equals to minus 2. So which is possible only if mod of OQ should be less than 1. So agar n equals to minus 2, if we'll see. So this point, if this point will lie here, so then your system will become unstable, because the condition is n equals to minus 2. So if it is stable, then it should be lying over here. In that case, OQ mod of OQ should be greater than 1, or K should be greater than 10.667. So range of K for stability is 10.667 less than K less than infinity. Thus for K equals to 10, the system is unstable. K greater than 10, thus for K greater than this 10.6767, system is unstable. Okay, thank you. These are the references.